Good afternoon and welcome to the Future of Finance's quantum computing discussion. Thank you for joining us. I shall now hand you over to Dominic Hobson and the panel.
Hello everybody, welcome to our webinar on quantum computing in financial services. I'm Dominic Hobson, co-founder of Future of Finance, and it's my privilege to moderate our discussion today about one of the most fascinating and certainly most important technology topics of our time, indeed at any time. David Deutsch, one of the founding fathers of quantum computers, defines quantum computation in his book, The Beginning of Infinity, as computation in which the flow of information is not confined to a single history. That would be a pretty weird observation in any field, save quantum mechanics. There, everything is weird. Waves act like particles and particles act like waves. Objects can be in two places at once. But it's precisely that weirdness that creates the opportunity for quantum computers to do what classical computers cannot. A quantum bit or qubit can register both 0 and 1 at the same time. So unlike the digital computers we're meeting on today, it can perform different computations simultaneously. That means their computing power increases exponentially with the number of qubits, 2 to the power of the number of qubits. So the potential power of these machines is immense. And what began in the 1980s as a purely theoretical concept in the minds of Richard Feynman and David Deutsch is now a set of engineering problems. Quantum computers are being designed, built, and operated. Since they can manipulate information for computations at the atomic scale, they're operating at the ultimate level of miniaturization. And miniaturization is, as we know, the main obstacle to sustaining Moore's law into the future indefinitely. Now, I've probably already embarrassed myself, and I'd certainly be flattering myself if I claimed to know how these machines actually work. But luckily for you, I don't have to flatter myself or embarrass myself further. Instead, I'm joined by 4 PhDs and 1 full professor, all with backgrounds in physics, and each of which has forgotten far more about quantum mechanics than I ever pretended to know. Dr. Mark Jackson is Scientific Lead Business Development at Cambridge Quantum Computing, an independent supplier of quantum software and algorithms. Dr. Francesco Correa is Research Lead at Boulderton Capital, an early-stage venture capital firm that has raised more than $3 billion for disruptive startups over the last 20 years. Dr. Ian Robotham is Client Technical Leader and IBM Quantum Ambassador in Financial Services at IBM. Dr. Jeremy Sosabowski is co-founder and CEO of Angler Dynamics, a financial markets forecasting company providing traders and asset managers with advanced warning of major directional market movements. Professor Bilal Ehsan Baki is a theoretical physicist now at the International Center for Education in Islamic Finance in Kuala Lumpur, after 32 years at the National University of Singapore, where he specialized in applying quantum mechanics to financial markets. Now, in addition to our panelists, we do, of course, also have you, our audience, and all 6 of us encourage everybody watching or listening to submit questions and comments throughout this webinar by using the Q&A or chat functionality at the bottom of the screen. Rest assured, we will not save them up to the end, but we will answer them best we can as we go along. We're now going to begin with a short presentation on quantum computation by Dr. Mark Jackson of Cambridge Quantum Computing. Mark, with that, I'd like to hand over to you.
Thank you very much, Dominic, and it's a pleasure to be here. I realize that we have a bit of a mixed audience and that not everyone is probably familiar with quantum computing, and so I prepared a few slides. So I prepared a few slides just to kind of briefly introduce quantum computing to people who might not be familiar with it. So this is what's usually referred to as the very first computer by Charles Babbage, exactly 200 years ago, and it happened to be in Cambridge, England. And even though it looks comically antiquated by today's standards, it actually has all the ingredients that we would identify with a computer today. It has input devices and output devices. And most importantly, it still processes information as on or off, which we now call ones and zeros. And so we've made a lot of progress in 200 years. This is a picture of the laptop that I'm giving this presentation on right now. And this is obviously much faster and it's much easier to use for the average person. And so it has all sorts of improvements, but it's still basically the same way that we store and process information. And what I'll be telling you about is the first advance in how we store and process information in 200 years, and that's because of quantum computing. These are a few of the terms that have been used, which you might have heard of. So the first is qubit, which stands for quantum bit. And this is the basic ingredient in quantum computing. So a qubit is to quantum computing like a normal bit is to normal computers, which we call classical computers. And the important difference is that a qubit can be a 1 and a 0 at the same time. Entanglement is this idea that the value of one qubit can depend on what the value of another qubit is, even if they're widely separated. And this is a purely quantum effect. There's no classical version of this. Superposition is the term where one qubit can be in multiple states at the same time, like both a 1 and a 0. And then the quantum advantage and such. This is a term which a quantum computer can do something that a normal computer can't do in any reasonable amount of time. And this was a milestone that was achieved about a year ago by Google, and it's now pretty widely accepted. And so this really shows that quantum computing has come a long way. This is why people are so excited about quantum computing. As Dominic mentioned in the beginning, there's an exponential increase in speed. Every time you add one qubit, you double the number of configurations that you have. So one qubit gives you 2 configurations, 2 qubits gives you 4 configurations, 3 qubits gives you 8, and so forth. So by the time you have 300 qubits, this actually corresponds to the number of atoms in the universe. So if you took the whole observable universe and you made a classical computer from that, that would be just as powerful as only 300 qubits. So even in principle, you couldn't build a computer more powerful than that. And so this is why people are so excited. It's not just that quantum computing is incrementally faster, like an iPhone 7 compared to an iPhone 6 or something. It's so much more powerful that we could use quantum computing to tackle problems that we never could have hoped to have tackled before. They really do exist. This is not science fiction fantasy buzzwords. So they really do exist. These are some pictures of actual quantum processing chips. There's a lot of approaches being used, like approaches like superconducting and ion trap and photonic and such. And these are some of the groups involved with building with each approach. And you'll see that there's big corporations like IBM and Honeywell and Google and such. There are some startups. There are some academic groups. And so there's a lot of approaches being used by many different groups here. This is a progress chart from just the past few years. And you've probably heard of Moore's law, which has shown that classical computers double in power every 18 months or so. Quantum computing is on an even faster trajectory. Quantum computing has doubled in power every 12 months or so. And the one metric that we use to describe quantum computing power, it's called the quantum volume, and it takes into account a lot of parameters like the number of qubits and the quality of the qubits and the coherence time and all these types of things. And IBM has been on a trajectory of doubling that every 12 months, so even faster than Moore's law. And that's that blue line there. The orange line is the progress that Honeywell has made. So they're on an even faster trajectory, and they believe that they can increase the quantum volume by a factor of 10 every year, at least for the next 5 years. So in just 5 years, we would be 100,000 times more powerful than where we are today. And then that lone yellow dot up on top, just a few weeks ago, a startup called IonQ announced that they think that they could have a quantum processor with a quantum volume of 4 million. And so that's several years ahead of schedule from where we thought we were. And that would be extraordinary if it's true. It just hasn't been tested yet. This is what they expect to have in a few months, and it just hasn't been verified by outside groups. But they're a fantastic group, and I have no reason to doubt them. And so we're well on our way towards making a lot of progress. So what would you do with a quantum computer once you start using it? These are some of the applications of quantum computing, and I could spend weeks telling you about each of these things. There's tremendous amounts of money and work being poured into this. Obviously, this is a financial forum, and so I kind of wanted to briefly touch upon some applications most relevant to the financial industry. The first thing I wanted to mention was algorithms. So in quantum computing, we develop these algorithms which can be much, much faster than a classical computing algorithm. And one example of that is in quantum Monte Carlo analysis. So Monte Carlo analysis is sort of a ubiquitous tool used to predict the value of some sort of commodity, because we don't know what things will be in the future. And so there's this randomness built into the algorithm to try to anticipate what the value of something will be. And quantum Monte Carlo is believed to be quadratically faster than its classical counterpart. So that means that if you run a quantum Monte Carlo algorithm for 1,000 times, you'll achieve the same level of accuracy as if you had run a classical version 1,000,000 times. So the more accuracy you want, the less you have to run it compared to the classical counterpart. And there's many other examples. I've just chosen one here, which is pretty well known, and a lot of groups are looking into this. These are some headlines from just the past year. So these are actual headlines I took screenshots of, and this shows how much interest there is from the financial sector. And so almost every major financial group has gotten into quantum computing in the past year or two. Many of them are setting up collaborations with quantum computing startups such as Cambridge Quantum. Some banks are setting up their own quantum group. So for example, Goldman Sachs, a few months ago, they poached one of the top quantum researchers to set up their own group. So they're completely self-contained now. So yeah, it's there's a lot of interest, and it takes time to develop these quantum software algorithms. So if you haven't already, I would strongly encourage you to get into the game. The second thing that I wanted to talk about was encryption. And this is sort of the one thing, if people have heard about quantum computing, this is the one thing that they have heard of. It's that it has something to do with hacking. And this is the reason. Most of the time when we communicate information on the internet, we're not sending the sensitive information itself. We're sending some sort of encrypted version of it, which means we apply some sort of complicated mathematical formula to turn sensitive information, like our credit card numbers, into some gobbledygook, and we transmit that. And then the person on the other end, the intended recipient, they can undo that formula with some sort of key. And that works pretty well most of the time. But we're having to revisit that because it turns out that the formulas that we chose decades ago happen to be formulas that quantum computing is really good at undoing. And of course, we didn't know that decades ago because there were no quantum computers. And we now see that there is a threat. Given the rate of progress of quantum computing the past few years, the threat of quantum computers to undo the formula, it could actually be in the near future. So it probably isn't today. We don't have quantum computers powerful enough to do that today. But in a few years, this could be a very real threat. And this is a chart showing what kind of threat it is. The top half of the screen shows the different formulas that are vulnerable to quantum computing. And that represents about 99% of the encryption that we use on the internet today. So this is a major threat to today's encryption. The bottom half of the screen shows some new approaches that people have been developing. So computer scientists and mathematicians have been developing new formulas which are not believed to be vulnerable to quantum computing. And I want to emphasize that we actually don't know the answer yet. This is a contest that's going on right now. An American government agency called NIST is holding a contest. People have been submitting formulas, and then others do their best to try to hack them. And just a few months ago, NIST released the 7 finalists. So it started as a long list of like 100 candidates, and it's now at 7. And so in a few years, they'll probably unveil the 1 or 2 winners. So that's the good news, that people are already developing new, what are called post-quantum encryption algorithms. But the bad news is that it takes time to upgrade. It's not simply a matter of you install some software and 10 minutes later, you're all good. If it's a complicated security system, like a corporation or a government agency, it could take months or even years to upgrade. And so that's why we're strongly encouraging groups to start upgrading their security system right now. Don't wait until you've been hacked, because of course, by then it's too late. And relating to this is a new type of encryption, which is completely based on quantum computing. And this is something called quantum key distribution. And so imagine you had some sort of source of entangled particles. So remember that entanglement is when the value of one qubit depends on the value of another qubit. And this is a purely quantum effect. So you have some source of entangled particles. The value of the qubit is random, but it's random together. And these are independently measured by 2 devices. We'll call them Alice and Bob. So Alice measures along some random direction, and Bob measures along a random direction, and they each get some answer, and then they compare notes. And if they measured in the same direction, they should always get the same answer. And that's because of this entanglement. So now Alice and Bob share a secret key, and they can use that for encryption, and it's known only to them. So now redo that story where there's some sort of eavesdropper. We'll call her Eve. So Eve is trying to be sneaky. Eve is grabbing one of the qubits, measuring it, and then replacing it. If this were classical physics, that would be the perfect crime because it's been replaced and no one would ever know the difference. No one knows that this eavesdropping has taken place. But this is a quantum system. And so Eve has destroyed the entanglement by doing that measurement. And so now when Alice and Bob, they do their measurement, they do all their measurements, and then at the end of the day, they compare notes again. And so even if they measure in the same direction, they're not guaranteed to get the right answer. Or sorry, not guaranteed to get the same answer as before. So you see that there's actually quite a few instances in which they got different answers. And so now when they compare notes, they see that something has gone wrong. And that's evidence of some sort of tampering or eavesdropping. They don't need to just trust that it's secure. They can actually do this mathematical check. And so this is a new method of communication which is completely secure. There's no way that you can get around this because of fundamental physics. And so this is a new type of communication, which we call quantum key distribution, and you're transmitting actual quantum data. And you can transmit this either along fiber optics or even with satellites. And even though this seems very science fiction-y, it's actually being done right now. There's networks being deployed in several countries, and China has actually already developed a quantum satellite to do this type of thing. So this will be very important to financial institutions for securely communicating. So that's a lightning introduction to quantum computing and some of the applications, including quantum algorithms and in quantum communication. We think that there could be advantages in just 2 to 3 years based on the amount of progress that we're seeing, that we could see commercial deployment of some of these ideas very soon. But it does take time. We're starting from scratch. You can't simply take your normal programs and run them on a quantum computer and expect them to be faster. It takes time to develop this. And so we're encouraging groups to start now. And so, so now I'd like to open up the panel for any questions that people might have and for discussion.
Thank you, Mark, for that very interesting introduction. I can't tell you how pleased I was to see that a quantum computer can do Black-Scholes calculations. I remember my first day at an investment bank nearly 40 years ago, where I had to calculate an equity option value using an HP 12C pocket calculator. It was not a great way to start. My investment banking career never really recovered. I'd like to begin really just by picking up another couple of threads and come first really to Bilal with a fundamental physical question, and then perhaps ask Ian about engineering problems. So if I said to you, Bilal, what fundamental physical problems remain to be, maybe a better way of putting this is, what is the physical obstacle to solving the engineering problem? What's the difficulty with quantum computing? And then Ian, I'd like to ask you just about, what's the remaining engineering problem that we need to come across from a more straightforward point of view. Bilal, you go first.
Good. Thank you, Dominic. Thank you, Mark, for a great presentation. Wonderful summary. The quantum computer is based on the idea of a qubit, as mentioned by Mark. Qubit is a quantum state. Now, you'd like this quantum state to be superposed with other quantum states, as was mentioned. Now, a superposed quantum state is a very fragile and a very delicate state of matter. Fundamentally, any kind of noise will disrupt it and break the superposition. And it is a superposition which is responsible for this exponential acceleration of the algorithm. So the first question is, how do you maintain this superposed state? So you come down to the idea of noise. So how do you deal with this? What happens if you disturb the system? You get error. So then you'd like to say, okay, I'll do error correction. I have this fragile system. I will let it evolve. I'll do my algorithm and I'll correct it. So then you have to recall from classical computers, what happens in practice is that every bit of a classical computer has 3 bits attached to it for error correction. To just illustrate it for you, if you transmit the same information 3 times, and you take the average of it, you tend to cancel out the error. So you have 3 bits for error correction. Now, in a quantum computer, you've superposed the two of these, these so-called 0 and 1 bits. So you have to transmit this qubit now. Now, the qubit has the normal 3 from the error correction for a classical computer And you have the superposition, which introduces another 3 qubits for its error correction. So it's 3 times 3 is 9. So conservatively, 9 qubits you require for error correction. But it's not over yet, because the quantum superposition is not about just transmitting the qubits, it's about the system being disturbed by noise from the environment. So, John Preskill, who's one of the pioneers and leaders in this field, he computed and he showed that you need 50 qubits to get one error-free qubit. So that to me seems to be a huge engineering problem, that how do you do the error correction? So he has suggested that most of the error correction should be done at the hardware level. You can try to correct it with the software also. So it's a fundamental engineering problem based on this fundamental physics of superposition being fragile.
Thank you, Bilal. Ian, perhaps I could get you to comment on that. You've heard Bilal say that the fundamental problem here is that qubits are extremely fragile, and you have to protect. And they're the superposition is responsible for the parallelism, so you have to protect it from outside influences. We read about quantum computers being in the deep freeze down at absolute zero to try and achieve this. Is that the type of engineering problem we're still dealing with quantum computers?
Yes, I would say so. And I think, building on what was said, and Mark touched on it, that there's different science that generates superposition. So in essence, we at IBM use superconducting circuits, there's trapped ion, semiconducting quantum dots, photons and neutral atoms, etc. And all of them will have their different challenges. Specific to IBM, I would say, in my experience, I split it into a number of categories. So one, the physical surroundings, as it were. You're quite right that we need extremely low temperatures down at absolute zero, minus 273 degrees Kelvin. That is a challenge in its own right. Any temperature increase above that can bring this a level of error in there as well, both noise and vibration even within the computer itself. Hence, that is a physical challenge. I think then when you look at the qubits and the chips themselves, actually placing one qubit next to the other, can cause a level of challenge and further error and noise. And then I'd say the next level of challenge is around the software that's interacting with the qubits as well. Software is continuously developing also, and you get a level of error in there. So I think in summary, it just shows, this is far from trivial. And everybody who's going about creating quantum computers has different challenges in different degrees. But again, just resonating on what Bilal said and Mark, that we use this quantum volume parameter. It's not so much about the qubits and watching the qubits go up. It is more about the quantum volume figure. Because this is showing you, in essence, simply put, how much compute power are you actually getting within a level of tolerance around error, so that ideally you can get to some form of fault tolerant calculation that you submit into the quantum computer itself.
We're starting to get comments and questions in. They're largely about what's happening in terms of real life applications in financial services. So I'll hold off on those just for a minute and come back to them once we've resolved some of these more fundamental problems. I was hoping to bring Francesco in, but he's disappeared from my screen. So perhaps there, you're back now. Hi, Francesco. I was just going to, you've been listening to the formidable physical and engineering problems which still confront quantum computing. You're looking to invest in this technology, indeed are investing in this technology. What makes you confident that it's going to get there, given those obstacles which we've just heard about?
Yeah, and sorry, Dominic, just I dropped out like in the exact moment that you were kind of pointing out to me. So as always, we talk about like AI, quantum, and all this stuff, but then eventually we drop down when it comes to connection and Wi-Fi. So I'm trying to echoing what Mark was saying before, what Ian was saying before. So the main thing that we are seeing also from an investment point of view is that we don't really know what's going to pay off right now, because there are so many approaches, so many things, and no one really this is very much like AI 10 years ago, where there were like a few things coming out of the dark of the 70s again, and we saw some light. So we saw something that was starting like to work, but no one really knew what was like the future looking like in 5 years time or 10 years time, right? So deep learning wasn't really like still a thing. I mean, it wasn't like a thing as it is today, at least. And there were like at least like 3 or 4 different things that might actually work out, which is like the same situation where we are today. So as Ian was saying, we have superconductors, we have trap ions, we have photonic qubits, and probably like silicon spin and then a couple of things, right? But the reality is that until we don't know what is really going to be like the best way to building qubits, that's going to be where an investment firm has both opportunities and challenges, right? Because we invest in things like potentially the exponential impact of this technology. I mean, this is great and we all recognize it and acknowledge that. But where the investment opportunity lies is in the fact that we are not sure 100% that one of these approaches is going to work, right? So if you actually pick it like the right one, that's going to be like a massive success. If we pick the wrong one, that's going to go like to zero, which is what happens like in investments like most of the time, right? But that said, honestly, I think that, and this is something that I'm going to say, which you probably already heard like multiple times in VCs and in like early stage investments overall. I think that like eventually, if you take outside all the technical development, which is crucial for this type of things, right? Eventually, I would probably invest much more in a specific team than a specific technology. I would be much more confident that if I pick like the right team that is working in quantum, which was something that Mark was saying before as well, these guys can pivot it to the right model when the moment comes, rather than like putting all my money on photonic qubits or whatever, right? I don't know if I'm making any sense or if any of the other fellow panelists has a different view on this.
Can I?
Jeremy, it'd be good to bring you. You've heard Francesco talk about this is like AI 7 years ago. Now, clearly, quantum computing can have a huge impact on AI. You're using AI to help financial services firms make predictions about market movements. What's the impact of it going to be there? And
well, just tagging on, by the way, Francesco, fully agree. We don't know the winners yet. We've picked a winner. I don't know if it's not strictly qubit based, but we've gone for the annealing one from D-Wave, live up and running. We're quite happy with it. Very much, we don't know the winners are. In our case, it works quite well, thankfully. We've got the right algorithm, so I'm not clear about that one. So I guess back to your question, Dominic, about sort of picking the winners. I do think it's the early bird catches the worm type thing. So maybe we haven't picked the winner. Doesn't really matter in our case. We're using it. We're okay. We're happy with it. We're sort of scaling up with it. So I'm mixed views about that. I wouldn't want to put my money. It's a bit like cloud providers, for instance. Yes, we're using Amazon currently, but we could switch to IBM, for instance, or we could switch to Google, basically. So it's just sort of what's the theme, what are the benefits, and then I'm separating technology. By the way, I'm a technology entrepreneur, but now it's very much business focused. So I don't think we need to pick a winner yet. That's my sort of simple answer, Dominic. So I don't know if I'm sort of skirting around your question really, but this thing about we have to pick a winner now, we're not sure what we're doing. It's like, well, there is already enough clarity as long as what the use cases are. So I'm very much open to comments, by the way. I don't want to monopolize this.
The question was actually, you're working with D-Wave because you think this can transform the ability of computers to search through vast amounts of data. Logically, if the power of these things grows exponentially, they can find stuff in half the time, right?
Pretty much, actually. And then we've enabled more services. We've done a bit more deployment. We have new forecasting capabilities, basically. So I mean, it's up to you guys. I'm just throwing it back, really. So there's probably enough out there. And back to Ian's point, yes, I fully agree. It's noisy. Like my background is photonics, by the way, photonics PhD. I think very noisy area. I'm not disagreeing, but treat it as an analog problem. The entire tech team in Cambridge is all engineers, actually, not computer science. I don't know why, but we're all sort of engineering background. It looks a bit like some of these analog computers. It's like, well, run it 1,000 times, run it 10,000 times, pick the peak, basically. That's probably good enough. So I think maybe we need to move away from this sort of digital type thing. And I'm not disagreeing, by the way. So, well, professor friend, let's try and do error correction. Well, good luck. Mm-hmm. Good luck trying to do error correction. So I'll stop talking now. Sorry, I have a...
No, don't worry. I wasn't trying to stop you. I'd like to address some of our questions here. But before I do, can I just ask, perhaps Mark, this is a good question for you. Is the short-term way forward here, or maybe the long-term way forward, some sort of hybrid between classical computing and quantum computing, or not?
Absolutely. So at least, so right now, we're in what we call a NISQ era, NISQ, Noisy Intermediate Scale Quantum. And that characterizes this era nowadays where we have quantum computers, they really work, but we don't have so many qubits that we can do this error correction, and they're not at the error level where error correction is beneficial. And so we have to keep the programs kind of small, and we can't use that many qubits. And so we have to be very mindful of such things. And in this NISQ era, we are definitely trying to use a hybrid approach, because whenever you're trying to solve a problem, we identify what would be most beneficial to run on a quantum computer and what would be most beneficial on a classical computer. That can do most of the heavy lifting. So we split the program into two parts and send those commands to those processors. They do their thing, and then the results are synthesized and integrated together. So it's a lot like a CPU and a GPU. We're now adding a QPU. And that will probably be a trend moving forward. You'll never use a quantum computer by itself. Quantum computers are not good at most things. What will happen is that the part that is good for a quantum computer will be sent to the QPU, and then the results are integrated at the end together. And so yes, right now we're definitely trying to develop these hybrid algorithms.
And Dominic, I'd certainly echo those comments. I think it's very much going to be an augmented world going forward. I mean, where quantum computing is infused into the digital world. I mean, similar to what we've seen in AI as well. AI is not totally replaced, humans by any means. It is now augmenting and supplementing them. So, for the better. So very much I see a similar view with quantum computing as well.
There's one question I must ask you, Bilal. How do you, before we start addressing some of these questions, how do you actually write code on a quantum computer? How do you tell it to store stuff and do?
Very good question. That's a loaded question, because many people have written code. You see, you go to MATLAB or you go to Fortran and you just declare the variables and you say A plus B C, end of story. It doesn't work like that for quantum computer. First thing is that you have to translate even say adding two numbers. Each number has to be translated into a qubit. So that's another, that's a first translation. Second thing, the gates, what I call gates in a computer, are these transformations which are matrices due to quantum mechanics. So every step in the algorithm, you have a matrix acting on the qubits. So now you have to decide, what do you mean by addition? So you have to then come up with a matrix which is based on laws of quantum mechanics, it turns out. And that will act on the qubit and make the process addition, something as frivolous as that, possible. So you may say, well, then how do I decide how to write the code? In my view, and we have so many experts here, I stand to be corrected if I'm wrong. We are at the very primitive stage of writing what we call machine language in the old days for the ordinary computer. We're actually working at the level of gates. Now, I'm a bit familiar with D-Wave, so I won't speak for that, but they use a tunneling process to find a minima. That's a different algorithm. But say for the digital ones, the Qiskit which IBM uses, these are matrices which are then put in sequence. And then you have something else which you never have in a normal computer. You have the act of measurement. You must decide which qubit will I measure, and that contains the answer with some probability. So all that the man writing the code has to know. Now, for me as a observer, if this is going to be successful, we have to develop a high-level language where all the stuff that I'm telling you need not be known. Like when you go to a computer, you don't talk about the bits or what the actual electrical engineering is. That is irrelevant. It's taken care of by the software. You just, what we call task-oriented software, like I want to design a house and I want to see how it looks, three-dimensional, I write the code. So for the quantum computer, presently the software and writing it is a major challenge because you have to be schooled in quantum mechanics to some extent. But the hope is that we must totally decouple from the software and hardware. The software should do its stuff and let the machine do the hardware. Specialists take care of that.
So we won't be giving the guy using Python in your middle office access to a quantum computer anytime soon.
Well, it's funny that you mentioned that.
Yeah, because Python is the language for writing,
It is.
But unfortunately, you must understand what to do with it. So Python is excellent. That's what's being used now.
But let me, if I may, just add to that. So, Bilal, you've mentioned, so IBM has QuizKit, yeah, that's the software stack that we use to integrate with our quantum systems. I took my 14-year-old son through some of the labs that were available, via the IBM Q Experience. And there is now a graphical interface as well. It's got Python sitting behind it, but he was creating quantum circuits all based on these labs. And he gets it. And I think it's really important that, the software developer of the future who are coming through our universities today, if not, some of them already in place, they will embrace this like there's no difference, as to what we did when a few years back when we were just starting off on our careers.
So I'd go one step further in saying that, we should totally decouple from the physics of the quantum computer. I'm a physicist, I love physics, that's not the issue. That's doing its job. The software should be decoupled from the hardware's intricacies and should perform the task that we wanted. So, I like what your son is doing because a lot of high school kids have summer school using Qiskit very successfully. So,
Okay.
Yeah, you're right. When you give them the software, they don't need to know quantum mechanics.
That's where we need to get to. It's like we don't even know how your car engine, your internal combustion engine works, as long as it does. Now, I'd like to get to the sort of nub of the matter now, which our questions and comments have been saying. I'll read the question and comments out. One from Peter Smith here. BBVA, Caixa Bank and JP Morgan Chase have announced or publicly discussed experiments involving quantum computing applied to use cases in 3 areas. BBVA has been pursuing the advantages of quantum algorithms in portfolio optimization of business size data sets, credit scoring, currency arbitrage, derivative valuations. His question is, what do you see arriving first? But he goes on to say, where are we at with quant computing in developments in financial services and fintech? Whilst quant is far from fully developed, there is a degree of focus on what role it can play in asset or portfolio construction and management. Portfolio optimization is not computationally expensive, but there'll be a lot of appetite for quantum simulation that can make any improvement, particularly when turnover transaction costs could represent 2 to 3% of assets under management currently. So he's drawing to our attention one very obvious use case in portfolio optimization, but he's saying that banks he's familiar with are using this also in credit scoring and currency arbitrage and derivative valuations as well. I don't suppose any of that surprises anyone on the call, but did any of you want to comment on that? Perhaps Jeremy, you had some thoughts about that.
I think Ian made the point is sometimes it feels a bit like AI 10 years ago. I don't know the details from all the banks. I'm going to give 1 or 2 examples here, especially what we're doing. It's a bit cynical. It's a bit like some of the banks were experimenting with blockchain at the time. Is this real? I don't know yet. The portfolio case is real, by the way. We've discussed that. We've touched that ourselves in our case. So I guess it's case by case. I don't know. I guess the banks, they're trying to future-proof themselves, right? We don't know which way it's going to turn out. So absolutely, I think they should be doing sort of in-house innovation, playing around with the technology. And I think the strongest use case will be in financial services. I think it's a no-brainer in terms of their computational requirements, complexities, optimization, forecasting, yada. And well, they've probably got the money too. So I guess I would say that running a growing fintech company, right, my money's on the banks. Well, I mean, finance in general, that's probably a driver of quite a few of the IT systems and infrastructure out there. So
okay, Ian, we have we have a question from another Ian here, Ian Hillier-Brook, who's saying presumably we already have real live use cases, i.e. not things just 2 or 3 years away. So Ian Robertson, could you address Ian Hillier-Brook to tell us, clients are actually doing things right now? I think we've clarified that, have we not?
Yes, so I mean, obviously, clients and picking up what Jeremy says, many financial services clients are showing significant interest in quantum computing. And we at IBM, we see our Q network growing and growing with the amount of members and partners that are getting involved. For me, we term it as we're still in a sort of quantum ready phase, and quantum ready really is, for me, the quantum computer is almost there with regards to performing as well as, let's say, some of the most powerful computational, classical computers. But we are now on the cusp of going into a stage that's called quantum advantage. And that's really where, the quantum computer starts to gradually get ahead and then hopefully accelerate off into the future. So I would, in answer to Ian's question, I suspect many financial services companies are trying to equate, right, is the output of a quantum computer based on some of the standard mathematical algorithms that exist today, is it as performant and fault tolerant potentially as what the classical calculation is? And they're probably level pegging, if not quantum's just catching up. Again, taking into account all the fault tolerant is a key aspect. Is it as accurate as what the classical computers are doing? But certainly coming in the next few years, I think everybody is the view that that's going to accelerate further. And hence, a lot of financial services companies need to start thinking about this, defining their strategies, starting to build quantum teams, within their organizations, so they're ready to take advantage of this when it does land.
Ian, while I have your attention, Ian Hillier-Brook has another question for you, not a related one, but he says it's not very environmentally friendly if you need cryogenics for these machines. And obviously that's important in today's ESG world. All these ESG funds will be running a mile if they think they have to inject all those carbon, whatever they're called, into keep the machine cool. How do you address that? Is his question.
I'd love to give the answer straight away, but no, it is a very poignant point that he raises. And actually, it was only this week that I was on a call where we were starting to discuss, when you look at the capacity of data centers today based on classical computers, how do we think they're going to look? And are they more economically friendly? Yes, there are some, demanding conditions that quantum computers need to run in today. But it's changing significantly. And again, studies are starting to take place now already, such that we can start to understand the environments. And dare I say, I don't think we can say that quantum computers will be less environmentally friendly. Again, when you start to think of their performance in the coming years versus that of classical computers, I dare say they may be better for the environment.
Okay, so I like your GPU analogy, Ian. Actually, like it'll be a sort of GPU type CUDA type thing. You sort of shift it off to the quantum side, and that's in. You get your results back, and you do a hybrid thing, which is, it's already happening, I guess, but just more of that, really. So yeah.
Francesco, a question for you from Anna Reitman on the idea of picking winners. Quantum computing and investment in it is likely to start being part of one hype cycle or another. Are you starting to see it? Which I think she means, are you starting to see a hype cycle here? What's the sentiment towards? She says, what's the sentiment towards media in the scientific community? But I'm not quite sure what she means by that. But the more important question is, are we entering a hype cycle here? Which stage of the classic Gartner hype cycle are we in? Are we in the trough of disillusionment, or the hillside of enlightenment, or I can't remember the phrase.
No, that's completely fine, and thanks for pointing the question out to me. I wouldn't to answer it anyway, and then also going back to what Jeremy and Ian were saying before. But to answer this specific question, my quick reflection, my quick insight is no, we are not in any hype cycle right now, and the reason why we are not there is because there are so many uncertainties around these specific fields that it's really hard to talk about hype cycle right now. So if you actually look at the numbers, honestly, across the entire globe, there are no more than 250 companies working on this stuff, which sounds like it's a great number, but the reality is that this is peanuts, right? There are only a bunch of experts in these fields. Some of the guys in this call probably are top-notch expert in quantum specifically. But the reality is that if you take probably 5 or 6 big companies, there are not that many startups working in this field. And honestly, you start talking about hype when you see like, specific funds coming over with a quantum thesis, or like a ton of different companies coming out of here and there. But the reality is that like the numbers are not still at that level. So if you actually look at Europe, there are no more than 60 companies doing quantum in Europe, like proper quantum stuff, right? In terms of investments, about like 100 million per year are deployed in early stage quantum investments. So like the numbers are not even close to to an hype cycle type of considerations. And honestly, I think that part of this is due to how complicated is this technology, and the fact that for many of these use cases that we've been mentioning, as Mark was saying before, quantum is not good for everything, right? Mm. So like first thing first, you have to understand what you want to use it for. And unfortunately, and I'm not sure whether Jeremy, I disagree with you on something. Probably I didn't understand correctly what you were saying before, but I'm not even like 100% sure that financial services is the main thing for quantum at this point in time. I mean, if you look at the last like 3 or 4 years, I think there were like 3 or 4 different industries that were taking up quantum before financial services, right? So material industry, chemistry, pharma and drug development, security, like there were like cases where quantum had a super straightforward impact, and people were, addressing all the forces there before going to financial services. Just closing up my tiny slot, Dominic, if you will allow me, just to try to answer to Peter, who was asking like a very specific question before. I think that Peter, to my knowledge, I know that D-Wave that the professor and Jeremy also mentioned before. I know that D-Wave has worked in optimal trading trajectory, so like all the dynamic portfolio optimization stuff. So that's already done. I know that there is one SDK toolkit made by 1Qubit that is working on feature selection for credit scoring. So all that, like PCA, HMM, all this stuff has already been done. Honestly, the stuff that Mark was mentioning at the beginning of this panel, which is all the, pricing of financial derivatives, all those things. I know that there is like a good academic literature on this topic, also on quantum applied to these things. So I know that some of the stuff can be solved, but honestly, to my knowledge, there are not that many companies working on that. I don't know if any of you knows of 1 or 2 specific companies doing specifically like pricing for financial derivatives.
I think briefly, just for transparency, we've taken venture capital, by the way, not from Boulderstone, Francis. We've taken it from Amadeus Capital Partners. So thank you very much. 3 bits first. I think you're just writing it down. Your initial comment, Francesco. You back the teams, by the way. You don't back the technology or the theme. You back the themes. I'm on that one. I think there's more money in finance, and fully agree. Chemistry and everything else. There's applications there, but I think in terms of the real mass mega market billions, I think it will be in finance and quantum. And I don't know, panel might disagree, but Ian, you might still get on that one. I think that's the point I want to make, really. So I think that's where probably the biggest money is in terms of use cases and everything else.
Can I just support Jeremy's view?
Please.
Because, to give you an example, let's, for example, take an engineering device like, say, solar cells. So there, the algorithm plays a very small part in the improvement of the solar cell. Most of it is hardware. In finance, on the other hand, if you have an algorithm which even improves by 0.1%, the impact is massive. My view is that the breakthrough in quantum computing will come from finance.
Yeah, I'm with you.
Because 2 reasons. The data is transparent. It's generated by the market. It's not through an experiment. And backtesting calibration is much more transparent than in an engineering device. And lastly, the money is there. And to come back to the point that was made by Mark, just since we are a finance, part of the technology here, 2 places I feel will have the highest possibility of success for quantum computer is portfolio optimization, where D-Wave is very big, and in arbitrage. If I may take a few more minutes, say a typical hedge fund, handling say $200 billion, they have an investment universe of maybe 10 to 20,000 instruments. And then they have to optimize the return minus the dispersion of the portfolio minus transaction cost with a constraint that the budget is limited. So to scan 30 years of data, you need a massive computing power. And something else the quantum computer can do, which classically you can't have, is to span the space of possibilities to catch the outliers.
It's okay. Well, that's what we're doing day in, day out. Sorry, you're doing our sales pitch here. Stop doing our sales pitch here, man. It's not fair. Come on.
But you know, I mean, the outliers normally a classical computer will not catch because it's far beyond the spectrum. So for these reasons, as for arbitrage, just to throw some numbers in, option, market is
on the option pricing. Oh gosh,
$650 trillion is the option market. Face value $12 trillion. If you can find arbitrage here, which is mispricing of tens of thousands of options, then of course you need a quantum computer. So for these reasons, although I'm all for other technologies, it seems to me finance is the place to make a breakthrough.
Okay, but Mark, I know you wanted to add something to what Francesco said, so go ahead. And I'd like you to think in the meantime, perhaps about this, Bilal. A question from John Spenceley: do quantum approaches potentially reduce the value of some current investing use cases? So think about that while Mark is adding to what Francesco said.
Sure. So I wanted to get back to the question of which of the many hardware platforms do we think is best, and where are we in the hype cycle and such. And so Cambridge Quantum develops software for quantum computers. And so a good question is, which ones have we chosen to develop for? And the answer is all of them. And the reason that we do that is because we developed a compiler which works on all the quantum hardware platforms. IBM, Honeywell, Google, Microsoft, IonQ, all the major ones that you probably heard of. All of the details of that architecture are built into the compiler. So the quantum programmer doesn't need to worry about it. They simply write their program, they indicate which platform they want to use, and the compiler finds the most efficient way to implement it on that platform that you've chosen. And so we don't know who's going to win the hardware game. We're very clear about that. We're hardware agnostic. And so we hear about progress being made and who's the hotshot and everything, and that's wonderful, but it's sort of like a marathon after 1 mile. We truly don't know who's going to win. And so we've hedged our bets, and so we have partnerships with all of them.
Thank you, Mark. And I'd like to come to Bilal about John Spencer's question now, but could you have a look, Mark, at a question from David Shropshire here about cybersecurity? I think we should come back to that. It's a very important one, and I'll come back to you once Bilal's given us a view on, is this technology actually to knock out some investment propositions, investment strategies that are presently making money?
That's a good question. A lot of money is being made on arbitrage in the New York Stock Exchange. I know that for sure. That will face fierce competition because you'll have this machine which will shave off the possibilities of arbitrage more and more. So a lot of arbitrage-based companies are going to have a new game they have to play. They can't play the old classical game. And I think also portfolio management, which is a massive part of finance, will radically change with the advent of quantum computers. Because you choose weights for your financial instruments, the quantum computer will choose them more efficiently. So classical portfolio theory and choosing portfolio risk management all will be affected.
Mm-hmm. Well, some of us think classic portfolio theory wasn't very good to start with, but
that's what I would say, Dominic. Thank you. Yes.
If I can add, Dominic, I'd also, fraud and AML is a huge area to go into, especially from a machine learning perspective. I mean, as those environments and ecosystems get extremely more and more complex, the more our financial services clients can do to eradicate fraud. Significant revenues there as well.
Which is a nice segue, Mark, into David Shropshire's question here, which is quantum key distribution seems like a major potential disruptor to the cybersecurity industry, as you said in your presentation very clearly. Does QKD require both parties to each have a quantum computer with an unbroken fiber optic cable between them? Would fiber optic relays impact decoherence? I really feel I understand that question now, having listened to your presentation. So
yeah. So that's a very good question. The good news is it doesn't require that you have a quantum computer for each party. but each party does need to have some sort of device to prepare the quantum state and then receive it on the other end. So you do need specialized equipment on both ends. Obviously, this isn't going to be something that individuals use for personal use or anything. This is going to be used by government agencies or telecommunications companies or financial firms. So someone who has a lot invested in keeping something secret. And so they would invest in this infrastructure of QKD. So along the ground, you would use fiber optics and you would have this equipment. To do longer distance over space, you can have satellites. And there are already satellites being built. So I mentioned that China has a quantum satellite that they launched a few years ago. And there's even a Singapore-based startup called Spectral. They have a CubeSat. So it's a very small satellite device, but it does QKD. And so what will probably happen is, like, we're having this exchange right now, which is using satellites and telecommunications and everything. The QKD will probably be hidden in the future. It will be done by the telecommunications companies. And so we will be communicating in chats like this using QKD. We just won't realize it.
Mark, can I ask you a question in the line of cybersecurity? You know, I read that the 2408 RS code, to break that, you need 20 million qubits. That seems to be a lot of qubits, you know, and to have them coherent to break the code doesn't seem to be around the corner.
So the question is this really a threat?
Yeah.
That's what I'm asking
Can I
you.
add to that afterwards? Actually, I've got some other use cases, but yeah.
Please,
Sure. So to give people the background, so as I mentioned in my presentation, we use these complicated formulas to do the encryption, and the formulas that we chose a few decades ago, they happen to be formulas that are easily undone by a quantum computer. And so the best known example is called RSA, and it's based on the difficulty of factoring numbers. So it's easy to multiply numbers together to get a bigger number, but it's difficult to go the other direction to figure out the prime numbers. And about 25 years ago, this MIT professor named Shor figured out how to do that efficiently using a quantum computer. Of course, the longer the key, the more qubits you need to undo that process. And so right now, RSA 2048, so you have about 2,000 bits for the key, you need many, many qubits. And that assumes that these were perfectly working qubits. And so once you add error correction and stuff, the number is something like 20 billion or something that you mentioned. So yeah, so it's based on that. It probably won't happen today. But here's why that might be a bit conservative for the number. So Professor Shor, he showed that it's possible using this algorithm. He didn't prove that this is the most efficient way. And so a lot of times someone will come up with a method just to show that it can be done, but then other smart people will step in and find better ways to do it. So Shor sort of had an existence proof, but there could be more efficient ways. And in fact, like some time ago, I saw a researcher at Google, he found a way to improve that by a factor of 1,000,000 or something. And so there's efficiencies that could be figured out. And second, there's other ways that people have been developing. I won't go into detail, but I think that the moral of the story is don't wait until you've been hacked.
Too late.
I encourage people to upgrade now. There's even rumors of hostile governments archiving things right now so that in a few years, when their quantum computers become powerful enough, they can unread everyone's mail. And it could still be embarrassing or harmful to you to have your mail from today read in a few years. So again, start upgrading now.
Jeremy, I'd like to. I know you want to say.
I'm dying because I've got something really on the money here. Sorry, pardon the pun.
Okay, go ahead.
Our team in Cambridge are actually great guys. They're currently using 2048 bits RSA. We could 10x, we could 100x the bits. Computing's cheap, so worst case scenario, our current, public-private keys, we can refresh them every 10 seconds. So, Mark, I disagree with you. I don't think it's a threat. I'm sorry.
So the thing about RSA with the public-private key is that it's exponentially faster on a quantum computer. So even if you double the length of the key, it's actually only marginally more difficult. And so that's why this whole post-quantum encryption system has been developed, because RSA will be...
This is recorded. We can replay it in 3 to 5 years' time, and let's see if things have changed. I don't know, whatever. I'll keep quiet now. So
Can I just so we leave the audience with some clarity on this point? If the whole of present day cryptography depends upon how hard it is to factor large prime numbers, and quantum computers can, in theory, if not yet in practice, factor large prime numbers in a matter of seconds, are we just saying that it's not a threat today, but it is likely to be a threat in the very near future? Mark, you're nodding.
Yeah, I would say that's exactly right.
You're not nodding. Jeremy, you still...
as I said, I'll keep quiet. We'll I think 3-5 years time we can replay this video and I'll eat my own words. I'm not convinced. I think classical linear von Neumann, whatever you want to call it, basically has a lot more mileage. I get it, public private, kind of defactoring yada yada type thing. Anyway, I'm not convinced. So I'll...
Okay. Well, Ian, do you have a view on this? Is it all over for classical cryptographic methods very soon or far in the future?
I think not immediately. I think it is a future thing. It's something we've just got to monitor. Yeah. So yeah, I'll sit on the fence, if I may, on that one.
Okay, we've had some more comments. But a very interesting question about qualia here, but I'll put that to one side. We'll come back to it. We're out of time. In fact, this is so fascinating. I'm going to carry on, irrespective of the audience is staying with us largely, so that's good. Just an observation about an anonymous attendee here to Jeremy's points. FPGA technology started in gaming and it only really gained visibility when finance got involved for algos and expedited its use because of the funding. I think that's a kind of observation about technology adoption. Here's an interesting question from James Green. At what point will computing speed outstrip transmission speed, and how much of a limiting factor is this? We've grown up in a world where algorithmic traders were parking their machines as close as they possibly could to the price source in order to gain an advantage. Do we have a similar problem of that? There's a kind of traffic speed limit in transmitting questions, I suppose, or data between quantum computers. So, Ian, is data transmission a problem?
Not data transmission, but integration of quantum computers. I think I was reading, in an IBM research paper that was published recently, and it was forecasting some of the challenges going forward, and if the integration sat there. So no, it's whether that manifests itself as network connectivity, I'm unsure, but certainly integrating these type of computers. In essence, they're in the cloud now, aren't they? I think we won't not personally own, but companies will not own a quantum computer. They will just access, these resources via the cloud. But yes, the integration of them is known to be, a challenge and something that will need to be overcome.
But the ultimate speed limit here is the speed of light, right?
Actually, I was going to throw this back. Actually, quantum tunneling and I don't know, some questions about that. Maybe some other time. Sorry, I don't know.
All right. We were all set, but could we perhaps, this is one for you, Bilal from Tiho Mochabaleli. Could the panel kindly comment on the role of qualia in quantum computing economic value propositions? Qualia are things like taste and smell, aren't they? Or am I misunderstanding that? What does qualia mean in this context, Bilal? Do you know? Has no impact?
No, I don't know. I can't. I don't know what qualia is referring to, actually.
Yeah. Okay. So, Tiho, we don't understand your question. Have another go at putting it back to us. But I think our panel don't think it has any impact on.
If it is what I think it is, actually, models of psychology. We are doing behavioral stuff, behavioral forecasting. Can we throw it back to the what's the exact question here? Sorry, I don't want to.
Yeah, I have put the exact question is. Could the panel kindly comment on the role of qualia in quantum computing economic value propositions?
Not sure. I'm going to leave that one. Sorry.
Yeah. I thought it meant can you program taste and smell, sort of things like that. Anyway, we are sort of about 5 minutes over our time now, so we should wrap up quite soon. But I'd like to just think about some of the longer term effects of this technology now, and I said to all of you before we started this discussion that this is a flavor of the Manhattan Project. And Mark, you've mentioned China having a satellite up there, which is capable of carrying these quantum keys. So there are geopolitical concerns around this technology, aren't there? Because the first person or the first country to crack it at scale will find themselves in a very, very powerful position. And we can think of regimes around the world we wouldn't particularly want to be in possession of this technology. It's a kind of difficult question for any of you, but where do you think these geopolitical security concerns, are they a constraint on this, on the private application of this technology? In other words, the ability of banks and chemical companies to make use of this is going to be constrained by government security concerns, rather as they were about the atomic bomb.
There was a story a few years ago about the PlayStation Sony was forbidden property because you could sort of reprogram it. I think we're beyond those days, Dominic. Sorry, I'm a bit simplistic here. I think this idea that sort of government tries to regulate and control things, and it doesn't quite happen commercially in practice, does it? So I don't know. I don't believe that's government. You know, the cat's out of the bag. Let's put it that way. I think we're a bit too late now to sort of try and have a sort of Soviet Union type technology, whatever, walls of whatever you want to call it, basically. So I think we're beyond that. So I don't.
Clearly, Bilal, quantum computing will affect all sorts of, including military technologies, will it not? Do we need to be worried about that?
Yeah, I tend to agree with Jeremy. You know, the example of Bitcoin shows you that the technology is out there, and it's very difficult to control this, especially because you don't need a very huge infrastructure to support this sort of undertaking. It's not a $100 billion initial investment. So a lot of private players can take part in it. I hope so. I don't want the government to put a brake on this beautiful technology anyway.
And what about, Bilal, what about the future of humanity? Does this
I'm glad you asked that. I tell you, I'm all for quantum computer, but I'm very worried about one thing, and I'm not an alarmist. So I want to discuss the connection of AI to quantum computer, right? AI is great. AI is about pattern recognition in huge database. A huge data set you have, it recognizes pattern by searching. Great. So here comes the quantum computer, enhances its ability to find patterns which were otherwise invisible. So then AI has two kinds, which many of us probably know, is artificial specialized intelligence and artificial generalized intelligence. Okay, so artificial specialized intelligence is you give a task to the algorithm or autonomous driving vehicles. Is you tell him, look, you take me to this mall, and he navigates and he avoids accidents. So he's fulfilling your task. The AGI, artificial generalized intelligence, decides its own tasks and has this enormous computing power. So here's a nightmare scenario. You have a weaponized robot who's AGI now. And that robot has computing power more than any other human being or institution. And this guy decides on the battlefield who lives and who dies. Maybe outside the battlefield, he decides who lives or who dies. And we as human beings can't compete with his computing power and with his speed at which he comes to conclusions. So how do you control this AGI? So I find AGI to be a bit frightening. Coupled to a quantum computer, we have this very simple example when IBM defeated all of these chess champions. So the machine learning, we didn't even know how he changed the program to defeat the opponent, who was a human being. We don't even know what he did. He kept on learning, changing, and then he won. He's in his own world, and he doesn't know how to communicate with us the changes he made in the algorithm to win this chess game. So AGI, I think as human beings, we should really be worried that if he sets his own agenda, this AGI, I don't know what he's going to do. That's my view.
Tiho has clarified what he meant by qualia. He meant feedback sensors, data from smart city demographics. Does that make it any easier for any of you?
Not particularly IoT person. No. I can't really comment.
I'm just making it more simple. I think it's a valid point that is raised there, but you need the mathematics and the algorithms, you know what I mean, to accommodate all these parameters in some type or form before you can apply a quantum computer to it, I would say. Yeah, so sometimes it's, you know, anything's feasible in some respects, but the mathematics needs to develop in parallel with the actual, you know what I mean, quantum compute power as well, for us to be able to incorporate these broader ecosystems of various different things, of which IoT is one of them that's been raised there.
Yeah, it was an IoT question. That's right. Well spotted, Ian. Thank you. I think we should draw things to a close, but could I ask each of you to, you know, just to round off our discussion, a sort of quasi philosophical question, which is, what are the other benefits we're getting from this technology? Are these machines helping us to understand quantum mechanics better? Are these machines taking us closer towards the sort of strong version of the strong version of the Turing principle says that any physically possible environment can be simulated on a computer. Are we learning more about how the world of quantum works, and are we moving closer towards a strong version of the Turing principle here? I'd just be interested in your philosophical thoughts to round out this discussion. Francesco, I don't know whether your blinking eyes mean that you're filled with illuminating thoughts about this, or whether you'd like to address this later. But if you
my blinking eyes were due to the fact that why you were asking this philosophical question. I was like going back to AI, but that's probably like because of my background, which is like is the same thing that like AI practitioner are wondering when it comes to deep learning, right? So we've been pushing this stuff, but the reality is that if you ask people, there are only like a bunch of individuals that really know what is happening like behind the scene. And if you actually see like around on the web or papers or reports or whatever, usually what happens is they give you like inputs that some sort of magic or black box that is happening, and then eventually outputs, right? Which is to some extent what is happening like today to quantum. So we want to see results. We want to see what is happening at the beginning, but no one really knows. I mean, no one, but you know, like a few folks know like all the things in between. So my blinking eyes were like trying to philosophically respond to you that I don't know, it's not like a black or white situation right now. I mean, it's something that honestly has to be. I don't know if Bilal, you were like raising your hands because you want to add something, but
well, Bilal can tell us whether we're learning more about the world of quantum from this technology.
Can I take the liberty of actually saying something on? See, I'm a quantum theorist and I've studied this many times. And you know, Mark made an observation which I don't know if people caught on to that. It was a stunning observation that after 300 qubits, the amount of memory stored and processed in a quantum computer is more than all the atoms in the universe. Mm-hmm. So I can make for you in a quantum computer with 1,000 qubits tomorrow. It's not that far. So question is, from quantum mechanical point of view, where is the computation going on? It cannot be in the physical universe. The universe doesn't have that many bits to accommodate that process. So you know what quantum mechanics says, which is stunning? Quantum mechanics says Hilbert space, where the place where things really going on for quantum mechanics, is a structure existing outside of space and time. Mm. That's what it's saying. The Copenhagen interpretation. Hilbert space is where things are happening. And so for me, as a quantum theorist, the most shocking thing about quantum computer was this Hilbert space was staring you in the face, that this is outside space-time. No matter of the universe, all the atoms cannot provide the number of classical bits that a quantum computer uses. So, you know, Mark made this tongue-in-cheek statement and he went on, and I was reflecting that, you know, can you imagine what he's saying? You know, what's going on? So that's immense philosophical message that quantum mechanics is giving us through the quantum computer.
I love that observation. but I'd like to give everyone a chance to say something. Jeremy, would you like to give us a poetic note on which to end?
I don't know why I'm being so practical engineer. It's like a GPU or a CUDA. It's another library. It's on the cloud and it does computing. And I hope that is today's conclusion. And there's lots of philosophy behind it. And I agree. And you could do space-time travel, yeah. But it's an extension. It's a library. It does computing. And hopefully people can go away with that. And the philosophy is nice, but let's be realistic, right? We have sorry, I hate to say it, but there's a few other pressing needs in humanity we might want to solve a bit soon. And if quantum can help, great. So let's just keep it real, keep it simple, please. Thank you.
Thank you. That's a practical point of view there. Ian, are you suitably down to earth, or do you have flights of fancy when you're reading these research papers?
I think huge advancements have been made and will continue to be made. I think you quoted Richard Feynman at the start, and what did he said? If we want to simulate the natural world, we need to make it quantum mechanical. So that naturally means we will progress in that field.
Mm-hmm. Thank you, Ian. Now, a last word from you, Mark, about this. You took us into this subject an hour ago. Now, wave us out with some startling observation.
My pleasure. So when quantum physics was being developed about 100 years ago, the mathematics implied that nature was fundamentally probabilistic, that there was no deterministic outcome of things. And that was kind of shocking to people because we had just taken for granted that if you had information, you could predict things. And back then, people truly didn't know whether that is how nature is, fundamentally random, or whether there were so-called hidden variables that we just didn't yet understand. And that's why it kind of appeared like it was random. But if we were smarter and figured out what these hidden variables were, then we could predict things again. And it wasn't until the 70s that we learned what the answer was. And it was this very clever physicist named John Bell who did an experiment to figure out the answer. And it turns out that nature is truly random. And this was based on quantum entanglement. And so when I was describing quantum communication, like QKD, that being able to communicate safely is based on this entanglement that's broken, and we can detect that. It just blows my mind that there's now a commercial application of this Bell's theorem, which is probably the most amazing thing in all of science, that nature is truly random. And we're now building these commercial applications based on that. And so I think it's amazing that we're now doing this and setting up little experiments in computers so easily.
Stupid question for you then, Mark. If Bell's theorem is correct, how can we be confident these machines are giving us the right answers?
That's an excellent question. And the answer is that if you write the algorithm well, then you'll get the right answer most of the time. But you're correct, you won't get it all the time. The trade-off in speed is that you're not guaranteed to get the right answer. And so that's why we usually run it several times and we look at the histogram and we check that that's the answer most of the time.
Mm-hmm. Anyway, I think we really had better stop there, but we can exit with an observation by a member of our audience, which is addressed to you, Bilal. Thank you for this last observation about the Hilbert space. And I echo that, and I echo what Mark said, and I echo what all of our panelists said. It's been easily the most interesting discussion we've had at Future of Finance ever, I think, and we'll definitely come back to this subject, as we always do, with more than our usual enthusiasm. But I think we really had better stop now. And I'd like to say thank you formally to our panelists, Dr. Mark Jackson, Dr. Francesco Correa, Dr. Ian Robertson, Dr. Jeremy Sosabowski, and of course, Professor Bilal Baki as well. And thank you also to the audience for your interest and your questions and your comments. Our next webinar is on Friday, the 4th of December, same time, same place, sadly, 1400 London time. It's on central securities depositories. So we're going from the sublime to something very different. CSDs, can they fix the blue screen of death they see in front of them? We hope as many members of our audience will join us then. But for now, it's goodbye from the 6 of us. Goodbye.
Thank you. Goodbye. Bye-bye.
Thank you, everyone.
Thank you, Dominic, and thank you to our panel. If you would like to see the summary of this discussion, please visit our website on www.futureoffinance.biz. And indeed, if you would like to see the video again, that is also on our website. Many thanks.